Hey folks, Ms. Gosling here. In this video, we are going to talk about circular motion, and gravity. By the end of the video, you'll be able to synthesize what you know about circular motion and gravity. So let's go ahead and get started. So I hope you have realized by now is that gravity can act, well, the Earth rotates around the sun. In this scenario, of course, gravity is acting as a centripetal force because it is causing the Earth to move in circular motion. When this happens, the centripetal force Fc is equal to Fg, or expanding out, Fg is equal to Fc. We know Fg is equal to g times the mass of the object generating the field times the mass of the object moving in the field divided by the distance between the two objects squared. And Fc is equal to the mass of the object moving times its speed squared divided by r. Now, one thing I want to point out is that when we talk about the mass in the centripetal force equation, that is the mass of the object that's going around. That's the mass of the smaller object, not the mass of the larger object. I could, of course, also write this as g times m is equal to mv squared over r. And what this means is that my gravitational field is actually equal to my centripetal acceleration. And this makes some sense, right? We've consistently used g as our gravitational field strength on Earth as our acceleration for objects in free fall. We're essentially doing the same thing, but this object is now in circular motion instead of free fall. Now, before I finish things, I do want to also just remind you that the period for Earth is 365 days, which is 365 times 24 hours in a day times 60 minutes in an hour times 60 seconds in a minute, seconds. The other thing I want to point out is that the speed for Earth is equal to 2 pi r divided by t, or 2 pi r divided by 365. And this is going to be true for any object in orbit. So with that, let's go ahead and look at an example. The following data are given for the moon. The mass of the Earth is 5.97 times 10 to the 24th kilograms. The mass of the moon is 7.35 times 10 to the 22nd kilograms. And the distance from the Earth to the moon is 384,400 kilometers. We are asked to calculate the orbital speed of the moon and show that the orbital period of the moon is approximately 27 days. So let's go ahead and get started. For part A, I'm going to start by listing my givens and unknowns. So I know that the mass of the Earth is equal to 5.97 times 10 to the 24th kilograms. The mass of the moon is 7.35 times 10 to the 22nd kilograms. And the distance between them is 384,000, or 384 times 10 to the third meters. And I want to find v, the orbital speed of the moon. So let's go ahead and take a look at my equation. Equation plus my substitution and my solution. So I have a few different ways I could solve this. But what I'm going to do is I'm going to go ahead and start with my equation Fg equals Fc. So what this means is g times the mass of the Earth times the mass of the moon divided by the distance between them squared is equal to m of the moon times v squared divided by r. Now we're going to use the mass of the moon on the right side because the mass of the moon is the object that is orbiting, and so that is the object that goes into my centripetal force equation. I can simplify this, and I can say that g times the mass of the Earth over r squared is equal to v squared over r, and I can actually say that g times the mass of the Earth divided by r is equal to v squared. So g times the mass of the Earth divided by r. Now, some of you may have also noticed, we also learned the equation g is equal to v squared divided by r. And so I could have just said g times the mass of the Earth over r squared equals v squared over r and skipped that whole step with canceling out the mass of the moon. I chose not to do that because I did want you guys to see both different ways to solve this equation. Regardless, I do end up with this equation down here. And simplifying it further, I get that my orbital speed is g times the mass of the Earth times the mass of divided by the distance from the Earth to the Moon, and the square root of that. Thus, v is equal to 6.67 times 10 to the negative 11th times the mass of the Earth, which is 5.97 times 10 to the 24th kilograms, divided by the distance from the Earth to the Moon squared, or divided by the distance from the Earth to the Moon. So that's 384,400 kilometers, or 384,400 times 10 to the third meters. I'm going to take the square root of that whole big ugly thing. And when I do this, I find, I'm going to go and draw a little arrow, I find that the velocity of the Moon is 1,018 meters per second, or 1,020 meters per second if I am putting this in proper sig figs. Now, one thing I do want to point out is that the mass of the Moon actually canceled out in my equation. So when I'm solving these problems, one thing that's important to know is that the mass of the object rotating in a gravitational field is actually irrelevant to the rotational velocity of the object. So if I took the Moon and I replaced it with a teacup, that teacup would have the same orbital velocity as the Moon, which is, I think, pretty profound. So we figured out the speed of the Moon. Let's go ahead and figure out so in part 2, I'm asked to show that the orbital period of the Moon is approximately 27 days. So let's go ahead and do that. So for part B, I'm going to start with my givens and unknown. I know that the speed of the Moon is 1018 meters per second. I know all of this other information about the mass of the Earth and the mass of the Moon and the distance as well. I'm not going to copy that down a second time. But let's see if I can go ahead and copy and paste it around. There we go. And we can just go ahead and cross off v equals question mark, because now I'm trying to find t. So I know from my notes about circular motion that my orbital velocity is equal to 2 pi r divided by t, because my Moon is going to go across the full circumference of its orbit in one period. So this means that my period is equal to 2 pi r divided by my orbital velocity v. And when I do this, because my orbital velocity is in meters per second, what I'm going to get is my period in seconds. So I'm just going to warn you of that. So in this case, my orbital period is 2 pi times 384,400 times 10 to the third meters, which is, is that a mouthful to say, divided by my orbital velocity, which is 1018 meters per second. Or putting that in my calculator, my orbital period is going to be 2,372,550 seconds. Now we are asked to show that the orbital period is approximately 27 days, so we do need to do some unit conversions here. So I know, let me go ahead and let's make myself a little space here. This is going to take a bit. So I know that I have 2,372,550 seconds. There are 60 seconds in a minute, 60 minutes in 1 hour, and 24 hours in 1 day. Therefore, putting this all in my calculator, multiplying across the top, dividing across the bottom, I get that this is that my period is approximately 27.5 days, which is of course approximately 27 days. Now, the reason that I wrote both my first line here and my second line here is when you are given an IB question that asks you to show something, before you give the final answer they're looking for, they would like you to give the answer with one additional significant figure, one beyond what they're looking for, to show that it rounds to the proper number. So that's just something I want to make sure y'all are aware of, because that is going to be my expectation for questions labeled show going forward. So with that, let's go ahead and talk takeaways. First of all, gravity can act as a centripetal force, and when it does, Fc equals Fg. So in other words, mv squared over r equals gmm over r squared. And it's very important to know the period of the Earth's orbit is 1 year, and the orbital distance is the circumference of the circle, which is 2 pi r. So with that, you now know all about how gravity can act as a centripetal force. It is now your turn to do some problem solving. Best of luck and happy working.